all the learning outcome that hopefully you should be able to achieve at the end of this lesson. Okay, the first one is draw and label the titration curve for the reaction between all these. Okay, for this acid-base titration, there are 4 types of titration. Okay, between strong acid and strong base, strong acid weak base, strong base weak acid, and weak acid weak base. So all these, okay, the titration curve is a bit differ. So we are going to look at all these one by one. Okay, and then calculate the pH at equivalent point for a given acid-base reaction. So we already done the calculation of pH for strong acid, strong base, weak acid, weak base, and salt. So in this case, it involving the reaction between acid and base. Okay, so in this titration. And then, and the last one of this 3.5 is for you to be able to select suitable indicators in acid-base titration. Okay. So hopefully you have already watched the pre-recorded video for 3.5. Okay, all the 3 videos. Alright, so in this 3.5, okay, this is the setup. Usually for acid-base titration, this is the setup that we do in lab. Okay, we have this unknown concentration of either acid and base in the flask. Okay, or we use you can use beaker as well, but then usually we use this conical flask to avoid spilling. All right, and then we put let's say if this one you put acid here, unknown concentration of acid. So of course this one you have to put base with known concentration. Okay, so that we want to determine how much the volume of base used to neutralize this acid. Okay, so by using lambatnya by using this formula. Okay, I know that you have learned this in your school days. Okay, but then okay, let's highlight again MAVA over MBBB, the formula to calculate neutralization. Okay, is equal to A over B. MA is actually for any general acid-base reaction, MA is the molarity of acid, VA is the volume of acid, MB molarity of base, VB volume of base, A, small letter A and small letter B represent the coefficients, stoichiometric coefficient for acid and base. So from this setup, okay, let's say you want to determine the molarity of acid by using the molar non-concentration of base and how much the volume used here. Okay, of course we already know how much the volume of acid that we put in the flask, so we can determine what is the molarity of that unknown acid. Okay, so this is the titration curve. Okay, so this one, if you look at the first and the second titration curve, okay, so it differ, the shape is almost the same, the S shape, but then the starting pH, if you look at the starting pH, this the initial pH start in the acidic range. Okay, but this one the initial pH start in the basic range. So from this plot or from this titration curve, we can predict that what is the species that we put in the flask. Of course, in this case, acid in the flask and base in the burette. Okay, but the other way around, if you set up the base in the flask and you put an acid in the burette, so you will get this titration curve. Okay. Alright, so if you notice this titration curve, let's say the first one, okay, you start with the acidic pH. After you add the base, the pH will gradually increase up to a point, okay, upon a small addition of base, the pH will increase rapidly. Okay, even though the volume you add just a small amount. Alright, so this in between this steep increase, halfway of that steep increase, the middle point of that is what we call as equivalent point. So when you do the acid-base titration and you plot this titration curve, the function that we plot this titration curve is that once we draw the curve from this steep increase, okay, the midpoint of the titration curve, that is what we call as equivalent point. So this one is the one that we want to determine from the graph actually. Okay. So here, okay, if you look at this, the pH at equivalent point for these two titration is pH 7. So meaning that the titration involving strong acid and strong base. Okay, because equivalent pH 7, okay, pH at equivalent point, which equal to pH 7, it only occur between titration of strong acid and strong base. Okay, so let's look at this later, the type of titration. Alright, and then what is equivalent point is actually from its name. Okay, equivalent point is when the number of mole of OH minus added equal to the number of mole of H3O plus originally present or vice versa. Okay, so the equivalent point with one pH value only. If you look at this definition, it is the number of mole. That's why the formula is MAVA. Okay, for any, let's say, one-to-one coefficient, HCl plus NaOH, for example, producing this salt and water and HCl plus water. So the coefficient is 1-to-1. So from the MAVA over MBBB equals to A over B. Okay, so we can get this formula MAVA over MBBB. MA, the unit for molarity is molar, mole per liter. Volume is liter. This one mole per liter. This one is liter. So when you cancel liter, mole of acid is equal to mole of base at equivalent point. So that's why upon achieving equivalent point, okay, we can predict or we can calculate the either of these two molarity by using the info that we have obtained. Okay, so let's say if you set up this one is acid, this is the base. Okay, so let's say this is the unknown concentration of acid just now. Okay, by using how much the volume used from the base. Okay, of course this one we pipetted, so we already know the volume. So you can determine what is the molarity of this acid. Okay, because the equivalent point is when the number of mole of OH minus added, okay, from the base here equal to the number of mole of H3O plus originally present, or vice versa if you set up the base in the flask and acid in the burette. Okay, and then we have another point in the reaction, which we call it as the end point. The end point is when the indicator changes color. So for any acid-base titration, we of course we have to put the indicator in the flask. Okay, so indicator, this is the function of indicator to determine the end point of the reaction. Okay, end point usually is just slightly after the equivalent point. Once let's say for this one, once OH minus a bit more extra than H3O plus originally present in the flask, so the color of the indicator will change. Okay, so this indicator should be selected so that its color change occur at pH close to that equivalent point. So of course, there are a list of indicator. So how to choose that indicator is actually okay. we are going to choose the indicator which pH close to that equivalent point of our titration. Okay, so in the range of pH at steep portion of the titration curve, what does it mean by this is actually, okay, this is the titration curve. So the steep portion inilah, okay, from this part to this part, usually kita punya indicator memang akan jatuh dalam pH range kat sini. Alright, so later we're gonna look at this indicator further in that part. Okay, ada indicator part. Alright, so for this curve, okay, titration curve for strong acid, strong base titration, okay, if you get this curve, meaning that your setup is the one that in the conical flask is the acid, okay, the one in the burette is the base, okay, because we start at the acidic pH. So the pH rises very rapidly at equivalent point. So if you look at this curve, okay, upon addition of sodium hydroxide, the pH gradually increase, but approaching equivalent point, it rapidly increase, and then up to here, if you add more base, okay, the pH gradually increase to a basic range. Okay. So what happened in this actually, okay, later we are going to look at this quantitatively, okay, by using the data. Okay, so in this case, if you have this acid here, okay, react with base, there is more there is still acid left here, okay, but then after equivalent, at equivalent point, let's say you have acid plus base produce salt and water. So at equivalent point, all the acid, let's say if you have 100 acid, 100 base, all the acid completely react, and there is none of these two species left at equivalent point because all react with base. So there is none for acid, there is none for base, but how much it is reacted, okay, will produce that much salt at equivalent point. Okay, and then after equivalent point, if you add more base, so the species present at that point is your salt and plus the base that you add. Okay, so later we are going to look at this in order for you to calculate the pH. Alright, so these are the types of titration curve. Okay, there are 4 types. Okay, if you look at this, the first one, strong acid, strong base, weak base, strong acid, weak acid, strong base, and weak base, weak acid. But okay, if you look at all 4 of these curve, most of the curve, the shape will be S shape, either starting from the pH base or pH acid, but then curve dia bentuk S, macam S. But for this one, weak acid, weak base, there is no significant shape because the reaction between weak acid and weak base, we can say that the pH at equivalent point is not obvious as well, meaning that we can predict what is the pH at equivalent point for this type of reaction. Okay, but for all the other type of reaction, we can predict the pH at equivalent point because depending on this, the type of acid base used. If it is strong acid, strong base, the salt that will be produced is neutral salt. That's why the pH is 7. Titration between weak acid, strong base, we do expect, okay, strong acid, weak base, we do expect the pH at equivalent point will be less than 7 because the type of salt produced is an acidic salt. Okay. Okay, let me write the example for you. HCl, strong acid, strong base, HCl, and EOH produce NaCl plus H2O. So this salt is a neutral salt with base strong acid. So we are going to use HCl plus ammonia maybe. weak base NH3. So it will produce NH4Cl. So this one is an acidic salt. Weak acid, strong base, for example, weak acid CH3COOH plus NaOH, for example, that will produce CH3COO, Na plus water. So this one, okay, both of them is weak base and weak acid. So okay, for example, you can use CH3COOH plus ammonia, for example. Okay, ni tulis sendiri dia punya produk. Alright, so this one, for weak acid strong base, the salt produced is a basic salt. That's why the pH at equivalent point is more than 7. So how do we calculate this? Okay, let's discuss on this pH. Okay, this is the summary between the type of titration and pH at equivalent point. This is actually where the steep increase of the pH that approaching equivalent point. So this is the formula that we have discussed. Okay, let's have a look on this example. Example, exactly 21 milliliter of 0.1 molar sodium hydroxide solution was required to completely neutralize 20 milliliter of H2SO4 solution. Calculate the concentration of the acid. So make sure for any reaction, do write the correct or the balanced chemical equation for this reaction. Okay, by using MAVA over MBVB, which equal to A over B. So in this case, the coefficient for acid is 2. The coefficient for acid is 1. The coefficient for base is 2. So plug in all the values in order for you to calculate the concentration of acid Ma. So by applying the formula, we can get directly the molarity of acid. Okay. Alright. And then the calculation of pH. Okay. So in order for you to calculate the pH, usually there are 2 points in the reaction that we want to determine the pH. Either the first one is the initial pH and the second one is pH at equivalent point. So for initial pH, you just have to determine what is the type of either acid or base present in the flask. Okay. In this case, if it is titration between strong acid and strong base, meaning that in the flask, the species present is strong acid. So how do you determine the initial pH for this acid? So recall back, how do you calculate the pH for strong acid? So strong acid, in order for us to calculate pH, we need the info negative log H3O plus. So of course we need this info. What is the concentration of H3O plus? For strong acid, H3O plus is equal to concentration of acid itself. So you can directly determine the pH. If you set up the other way around, the base in the beaker or in the flask, okay, how do you calculate pH? Okay, you need this info first, the concentration of hydroxide ion. So for any strong base, the concentration of hydroxide ion depending on your concentration of base. Okay. So after you get the concentration of hydroxide, you can calculate POH and then you can calculate pH by subtracting by 14. Okay, so that's how you calculate initial pH. You just have to determine what is the species present in the flask. Okay, and then pH at equivalent point for strong acid strong base titration, you tak perlu kira pH dia memang 7. Kenapa? Okay. Okay, let's have a look on this reaction. Strong acid HCl react with strong base. Okay, this reaction produce an ACl, a neutral salt. When you construct this ICE table, Okay, for example, this one. Um, okay, let's go through this one. Okay, why the pH is 7? Okay, titration of 25 milliliter of 0.1 molar HCl with 0.1 molar sodium hydroxide. Okay, so um, in order to achieve equivalent point, okay, if you use this MAVA over MBVB, which equal to A over B, you will get the volume used for base is 25 milliliter. Okay, because the same concentration of acid, we do expect the same volume. Okay, because the reaction is 1 to 1. Alright. So, and then, okay, in order for you to calculate the pH at equivalent point, okay, we need to set up this mole table. Usually, when we construct the ICE table, we use the info molarity, but for titration, we are going to use mole. Why? Because recall back the definition of equivalent point, the number of mole of OH minus added must be equal to the number of mole of H3O plus present. So, so from this info given for you, you can calculate the number of mole, the initial mole of HCl. 0.025 liter times the molarity, this is the number of mole for acid. Okay. To reach equivalent point, because we need the same amount, you have to add, okay, construct this ICE table for mole. Okay, this is the original mole present in the flask. So you have to add the same amount of sodium hydroxide. Okay, so if you add the same amount of sodium hydroxide, it will react completely with HCl. So the final mole of this reaction, okay, will be 0 for HCl because it completely react with sodium hydroxide. Sodium hydroxide will be 0 as well because it completely react with HCl. But then the same amount, how much this acid and base reacted, the same amount of that salt will be produced, okay, and HCl. So in that point, during equivalent point, so the species in the flask yang tinggal hanyalah NaCl. So if you recall, NaCl dissociation will produce Na plus and Cl minus. None of these two ion that will further hydrolyze in water. So the pH of this is neutral, okay, which equal to 7. Because none of these ion that will further hydrolyze in water. Do you still remember that? So it's actually for this titration, how you calculate the pH at equivalent point is actually depending on what type of salt produced. Okay, so recall back how do you calculate the pH for salt, then settle for titration. Okay, do you have any questions so far? No? Alright, so I assume semua faham
Faham itu.
Alright. Okay, so this one, okay, this one, the volume for NaOH, okay, kita perlu volume for to calculate pH kalau titration tu adalah between strong and weak. Okay, kalau weak, strong dengan strong, kita tak guna pun kita memang boleh tahu dia punya volume, dia punya pH is 7. Alright, so this is the checkpoint for this one. Okay, calculate the volume of 0.5 molar NaOH need to be added to, to 50 milliliter of 0.25 HNO3 to reach equivalent point. So just apply MAVA over MBVB, you will get this volume. Predict the pH at equivalent point of the solution in A and explain why. So the pH will be 7 because strong acid and strong base are 100% ionized in water, or you can say that this the salt produced is a neutral salt where all the two ionized ion will not further hydrolyze in water. So the pH will be neutral 7. Okay. Alright. And then the second type of titration is in between weak base and strong acid. Okay, so this is the example here. You have HCl and ammonia. This is the salt produced. So the salt produced, this is the salt dissociation. NH4Cl produce NH4 plus and Cl minus. Okay, in order for us to calculate the pH, at equivalent point, you just have to consider this salt, okay, because we know that there is none of these two species left at equivalent point. So NH4Cl dissociate to produce NH4 plus and Cl minus. From these two ion, NH4 plus will further hydrolyze in water, okay, to produce this H3O plus. That's why pH at equivalent point is in acidic range, okay, less than 7. So in this case, the species present in the flask is actually the base, and the one that you put here is the acid. Okay, because you start with basic pH. So okay, the calculation for this weak base and strong acid titration. Okay, since the one that you put in the flask is the weak base, okay, the initial pH, how to calculate pH at initial? So we use the steps to calculate pH for weak base. Alright, so you need the Kb info. This base in water will produce conjugate acid and OH minus. So find this OH minus by using this formula, square root C. This is the C actually. Okay, the concentration of this base times Kb. Okay, square root of that, you will get OH minus. After you get OH minus, convert to POH and then convert to pH. So you just need to recall how to calculate pH for weak base. Okay. And then pH at equivalent point. So at equivalent point, just like I mentioned just now, the species present is only your salt. This is the salt dissociation reaction, and this is what happened. Okay, from this salt in water, it will further hydrolyze to produce this ammonia, dapat balik ammonia and H3O plus. But okay, when you construct the ICE table for this reaction, okay, in order for you to calculate the pH, yes, you need how much the concentration of hydronium ion. How to get this? Okay, is equal to square root C times Ka. The C, okay, you need the concentration of this species. Okay, how to get the concentration of this species? It's actually the same as your salt because it completely dissociate. If you have this salt 1 molar, maka NH4 plus is 1 molar and Cl minus is 1 molar as well. So the concentration here is 1 molar that will further hydrolyze to produce this ion. Okay. And then how you get this molarity? Balik kepada reaction yang asal. Okay. This reaction, if you construct the table like this one, okay, 25 milliliter of, sekejap. Okay, so you use 25 milliliter of 0.1 molar ammonia and 0.1 molar HCl. So the reaction is 1 to 1. We do expect 25 milliliter of HCl. So in this case, okay, when you construct the mole table, you know that this is the initial concentration of ammonia. You have to add the same amount of HCl and the same amount of NH4Cl will be produced. But this is in number of mole. To get the molarity, you must divide by total volume. Okay. Total volume in this case is 25 plus 25 because you use 25 milliliter ammonia and 25 milliliter HCl. That's why you need, before you start the pH calculation, you need to determine how much the acid used in volume. Okay, because later after you get the number of mole of salt produced, you need to divide by the total volume of acid and base to get the molarity of salt. Okay, so after you get the molarity of salt, use in this to get the H3O plus. Tadilah, okay, katalah after you calculate the molarity of salt, you get here 1 molar, and then here 1 molar, produce 1 molar, 1 molar. This will be used in this equation. So because the concentration of H3O plus is equal to square root yang biasa kita guna C times Ka, this C yang kita nak tadi. Okay. So inilah ni, this is actually the summary of, you can use for any type of acid and any type of base, in this case, okay, weak base strong acid. So to get the Ka value for this NH4 plus, usually in the question you will be given the Kb value for ammonia. So make sure find the Ka value for NH4 plus by using Kw divided by Kb. And then after you get this, H3O plus convert to pH. Okay, let's look at this example. Okay, calculate the pH at the equivalent point for 25 milliliter 0.1 molar ammonia titrated by 0.1 molar HCl solution given the Ka for ammonia. Okay, so first thing you have to write this balanced chemical equation between reaction of ammonia and HCl to produce this salt. And then second, you need to determine how much the volume used for HCl, okay, by using MAVA over MBVB is equal to A over B. And then after you get that, convert the initial ammonia, okay, to number of mole in order for you to set up this mole table. Okay, once you dah set up this mole table, okay, the number of mole obtained for this salt, okay, must be divided to total volume. So in this case, the total volume is 50. Alright. So currently in your system, in your flask, okay, you have NH4Cl sebanyak 0.05 molar, that much. Okay. So next step is for you to calculate pH macam kita calculate pH for salt. Okay. So NH4Cl dissociate to produce NH4Cl, NH4 plus and Cl minus. Notice here the arrow used is wrong because dissociation of salt is 100%, meaning that fully dissociate in water, you need to use a single headed arrow. But for hydrolysis of salt, yes, this is correct. Okay. Okay. So once you have done this salt dissociation, produce NH4 plus and Cl minus. Okay. Consider these two ion and determine which one that will further hydrolyze in water. So in this case, NH4 plus will further hydrolyze in water because it is conjugate to a weak base. So sifat dia itself is a strong conjugate. Okay, sebab dia conjugate kepada weak, maka dia adalah strong. Cl minus conjugate base kepada strong acid, maka dia adalah weak. That's why dia tak further hydrolyze in water. Hopefully you can remember that. So NH4 plus in water, ni you boleh letak sebenarnya water. It will produce ammonia and H3O plus. Kalau you letak water, sini dia akan jadi H3O plus ya. Tapi dua-dua tak salah pun, nak letak mana-mana boleh. Tapi usually to make it easier, okay, tak nak be confused, you just letak water. Alright, so once kita dah dapat tadi the molarity for this NH4 plus, construct ICE table. 0.05 minus at 00 plus at equilibrium. This is the data that we need. Okay, so by using Ka, so Ka is equal to macam biasalah product the dissociated ion H plus time NH3 divided by NH4 plus. This is the original concentration of NH4 plus. This is the Ka. Okay, ni Ka yang kita nak tadi ya. You are given in the question is Kb for ammonia, but we need the Ka for this ammonium ion. So find the Ka first and then solve for X. After dah dapat X, dapatlah pH. But then of course, there is always alternative method in order for you to calculate the H3O plus. Okay. So kalau tak nak construct ICE table, untuk yang tu pun boleh. H3O plus is equal to square root C times Ka. So C, the one yang kita kira for salt. Ka, carilah daripada Kw tadi. Ka is equal to Kw divided by Kb ammonia to get the Ka NH4 plus. Okay. So you will get the same value. H3O plus is this much and then convert to pH. Faham tak?
Faham, Madam.
Faham Ada soalan nak tanya? Tak ada? Alright, well done. Alright, the second example, 20 milliliter of 0.115 CH3NH2 solution was titrated with 0.1014 molar HNO2. Calculate the pH at equivalent point given Kb for this one is 4.4. So this is a weak base, knowing that you are given the Kb for this species and titrated with strong acid HNO3. So construct this equation, the balanced chemical equation between this weak base and strong acid. Find the volume of the acid used and then get the number of mole for the base present. Construct this reaction. Okay. Construct the mole table, the original mole present, how much HNO3 added, and how much the salt produced. Okay, so after you get this number of mole, find the molarity by dividing by total volume of acid and base. Okay, after you get the molarity, either you want to construct the ICE table or you can directly use the alternative method. Okay. So okay, kat sini salah Kalau you tengok dia punya base dan juga acid CH3NH2, HNO3, CH3NH2, HNO3, okay, bila dia jadi produk, dia akan jadi CH3NH3 NO2. Okay, dia terlebih satu. So ni tambah je kat sini. Ni sama case macam you bayangkan kalau ammonia react dengan HCl, dia akan jadi NH4Cl. Sama case lah. Okay, you just tambah benda ni kepada ammonia. Alright, so ini betul. Okay, dah dapat salt. This salt dissociate, pecahkan je balik kepada cation dan anion. So it will produce this CH3NH3 plus betul, NO3 minus betul. Okay, so once you dah dapat ni, pilih either one of these that will further hydrolyze in water. So this one will further hydrolyze in water. Okay, ni tertinggal water, H2O. Okay, so yes.
Saya macam bila kita nak tentukan yang mana yang akan hydrolyze, kita tengok dekat conjugate ke, Madam?
Betul. Kita tengok dia conjugate kepada siapa. Kalau dia conjugate kepada weak, yes, dia boleh further hydrolyze in water. But kalau dia conjugate kepada strong, maka dia tak boleh further hydrolyze in water.
Oh, okay.
Contoh NO3 minus, dia conjugate kepada strong, HNO3, which is a strong acid. Maka dia adalah sangat weak, so dia tak boleh further hydrolyze in water. Ini conjugate kepada weak. Macam mana kita tahu dia weak? Dia bagi tadi Kb dalam soalan. Dia bagi Kb benda ni. So kita tahulah partner dia ni weak. Maka this is strong enough to further hydrolyze in water.
Okay, faham, Madam. Thank you.
Alright, okay. So once you construct this hydrolysis reaction, produce H3O+, so kita boleh cari H3O+, guna sama ada nak construct ICE table or you can use this simplifying method. Okay. So H3O+ is equal to square root C times Ka. So this is the C that we obtain. Okay, for the salt. And then Ka, ni lah. You kena cari what is the Ka for CH3NH3 plus given in the equation Kb CH3NH2 by using this formula. Dah dapat dia punya Ka, masuk dalam ni, dapat H3O plus, then you can calculate pH. Okay. So konsep dia samalah. Maksudnya you just sampai ke salt and then salt tu you perlu dissociate and then pilih which ion that will further hydrolyze in water. Okay, so later try to do this checkpoint. Okay, checkpoint 15. Okay, and then calculation of pH, weak acid and strong base. So yang tadi kita titration yang kedua adalah weak base strong acid, but this one the other way around, weak acid strong base. The concept is just about the same with the second one that we have discussed, but then this one strong base weak acid, maka you akan dapat salt dia adalah basic salt. So bila you dapat basic salt, and in order for you to calculate pH, you akan kira menggunakan OH minus. So you akan dapat POH, baru you dapat pH. Okay, so OH minus of course square root C times KB, maka you dapat POH negative log OH minus, and then baru you kira 14 minus POH to get the pH value. Okay, so let's look at this example. Okay, the reaction between weak acid CH3COOH, acetic acid, and sodium hydroxide, which is a strong base, to produce sodium acetate. Okay, sodium acetate in water will produce acetic ion and sodium ion. Between these two, okay, acetate that will further hydrolyze in water, sodium will not, okay, because it is a conjugate of a strong base and AOH. This one conjugate of weak acid, it is strong enough to further hydrolyze in water. So this is hydrolysis equation of acetate ion in water that will produce OH minus and CH3COOH, the acid, the original acid yang kita guna tadi. Okay. So this two calculation involved in strong acid, strong base. Okay. So initial pH depending on what species present in the flask. So in this case, you letak weak acid dalam flask. Okay, because you start dengan pH weak acid. Titration between weak acid and strong base. So strong base dekat dalam burette. So to determine the initial pH, weak acid guna konsep yang sama macam you kira pH weak acid. Okay, so H3O plus is equal to Ka C times Ka, square root C times Ka. So Ka for weak acid, concentration of that weak acid, dapat H3O plus, convert to pH. So suppose there is no issue there. And then pH at equivalent point, this is the reaction. Okay, this generalized equation, this is the example that we use from the previous slide. Okay. So CH3COOH react with NaOH, produce this salt. This salt dissociate to produce this ion that will further hydrolyze in water. So you akan produce OH minus. So to calculate the OH minus is equal to square root C times Kb. C is the concentration of this that you get from the concentration of salt. Okay, so concentration of salt you dapat daripada mole react dengan mole and the same number of mole divide by total volume untuk dapat molarity of salt. Sama macam case tadi lah. Okay, dah dapat molarity here. If here is 1 molar, this will be 1 molar, this will be 1 molar. So this further hydrolyze. So the concentration of acetate ion will be the same concentration as your salt, sodium acetate. Okay, so this is the C that you get from the salt. Okay, Kb, of course in the question you will be given the Ka for acetic acid, usually CH3COOH, Ka. So you need to find what is the Kb for this CH3COO minus in order for you to use this formula. Okay, once you get this hydroxide concentration, find the POH and then find the pH. Okay, so the concept is just almost the same as the second one, but this one it changed to weak acid strong base. The previous one weak base strong acid. Okay, so let's look at this example. 25 milliliter of 0.1 molar sodium hydroxide reacting with 25 milliliter of 0.1 molar CH3COOH. In the titration, calculate the pH of a solution given the Ka for CH3COOH is this value. Okay, so step 1, find the number of mole. Step 2, construct this mole table for this titration. CH3COOH and AOH, this is the salt produced and water. Okay, how much the acid present, that much you need to add for base. Okay, at the end of the reaction, there is nothing left for acetic acid and sodium hydroxide, but then how much it is reacted will produce the same amount of salt. Okay, say after you dah dapat number of mole for salt, divide by the total volume to get the molarity of salt. Okay, after you get the molarity of salt, okay, construct this equation to show that this ion further hydrolyze to produce OH minus and CH3COOH. So after you construct this, you can use the formula OH minus is equal to square root C times Kb. C is the one that you calculated for salt. Kb is, find what is the Kb value for acetic ion. Okay, by using Ka value of acetic acid. After you get OH minus concentration, calculate POH, negative log OH minus concentration, and then you can calculate pH. Okay? Is there any question regarding this?
Madam,
Yes?
yang nak cari step 2 tu kan, yang nak cari
Step
concentration of salt tu, kalau saya tak buat table tapi buat macam ratio boleh ke? Sebab dia kan
Sama je.
coefficient dia 1, 1, 1 kan?
Boleh je.
Boleh.
Tapi just to show you, this one, biasanya kita buat because kita nak tengok kalau dia memang 1-to-1 then okay lah. Ada certain reaction kadang-kadang dia bukan 1-to-1, so kat sini lah you kena sama ada darab 2 ke. Tapi kalau you memang tahu dia adalah 1-to-1, you tak nak buat ratio, you cakap okay, the same amount of salt will be produced. Boleh je, tak ada masalah.
Okay madam, thank you.
Alright. Okay, is there any other question before we proceed? Tak ada Alright, so do try to answer this checkpoint. Okay, checkpoint 17 as well. And then you have this pH indicator. So indicator, acid-base indicator is a weak organic acid or a dye whose colour differ from its conjugate base. So dia sebenarnya adalah acid-base indicator. Dia sejenis weak organic acid. So initially colour dia katalah contoh macam phenolphthalein. Let's say the colour initially is colourless, but then once dia tukar daripada, once dia tukar kepada dia punya conjugate base, colour dia akan tukar kepada pink. So since dia adalah acid base indicator, once kita masukkan dalam kita punya reaction, at some point dia akan tukar kepada dia punya conjugate yang memberi colour yang berlainan. So that's how indicator works. Okay, so many dyes change colour depending on the pH of the solution. So that's why we are going to choose the suitable indicator based on its pH range. Okay, so an indicator can therefore be used to determine the endpoint of the titration. That's why we use indicator, and how to choose is this one. The pKa of indicator must be approximately equal to the pH at equivalent point. So let's say we know, we already predict what is the pH of equivalent point of our titration. So how to choose the indicator? We choose the one that having pKa value approximately equal to the pH at equivalent point of our titration. Okay, so it changes color within the same range as the rapid change in the pH. Okay, these are the list or the example of indicator and its color at this pH range. Okay, so you boleh tengok ya kalau you punya titration dia punya steep increase. Okay, mana gambar? Tak ada Oh, tak ada. Alright. So kalau you contoh, kalau you tengok dia punya titration, this is where you punya steep increase for pH yang ada equivalent point. So mana-mana indikator yang jatuh dalam range ni, yang saya bulat ni, range ni boleh digunakan. Okay, so you tengoklah kat sini. Dia punya pH range. So apa-apa yang jatuh dalam range ini boleh digunakan sebagai indicator for that titration. Okay. So this is the color change and you boleh tengok dia punya pH. This is indicator as well. Yang ni dia bagi siap-siap dalam bentuk macam ni lah. What is the color change and what is the pH range for color change. Okay. So you just have to choose. Alright. Is there any question for 3.5 before we proceed to this buffer solution? No? Okay, so next, moving forward to buffer solution, the last subtopic for acid base. Okay, so this one we are going to watch the pre-recorded video first and then I'm going to explain a bit on the important part of this buffer.
These are the learning objectives of this subtopic. And under buffer solutions, we are going to learn on the types of buffer, common ion effect, pH of a buffer solution, and finally effectiveness of a buffer. Okay, now let us look at the first subtopic, which is types of buffer. So what is a buffer solution? It is a solution of weak conjugate acid-base pair. So in a buffer solution, okay, there are two components that must be present. The first one is a weak acid or a weak base, and the second one is its salt. So buffer solution resists changes in pH when small amounts of acid or base are added to it. So for your example, there are two types of buffer. Okay, the first one is acidic buffer and the second one is basic buffer. So for acidic buffer, okay, it is a mixture of weak acid and its conjugate base. An example of an acidic buffer solution is a mixture of acetic acid and acetate ion, which is from the sodium acetate. And for basic buffer, it is a mixture of weak base with its conjugate acid. Okay, so an example of a basic buffer solution is a mixture of ammonia and ammonium, which is from ammonium chloride. So you can see here that in the buffer solution, they contain both an acid base species. Okay, now students, let us look at this diagram of a formation of a buffer. So as I mentioned earlier, a buffer must contain significant amounts of both a weak acid and its conjugate base, or vice versa. A buffer system can be represented as salt acid or conjugate base acid. Okay, let us consider the simple buffer made by dissolving acetic acid and sodium acetate. So once it forms a buffer solution, it will form several ions. Okay, and since weak acid is partially ionized, it will form as an acetate ion, acid, as well as the hydronium ion. And for sodium acetate, it will ionize to form sodium plus and acetate ion. So now let us look at the applications of buffer, or the importance of buffer in our body. Fortunately, you have buffer in the blood to protect against large changes in pH. So for information, the buffer in blood is composed of carbonic acid and its conjugate base, which is hydrogen carbonate. And this buffer system keeps the pH of the bloodstream at a neutral 7.4, as any deviation from the human blood can have extremely disruptive effects. So for the second point, hemoglobin also acts as a buffer in the blood. So during exercise or increase in metabolic activity, so this hemoglobin helps to control the pH of the blood by binding some of the excess protons that are generated in the muscles, okay, so that the body can use the oxygens. And for commercial products, we also have buffer system in shampoo and baby lotion. And for shampoo, it contains buffers of citric acid and sodium hydroxide, which work to balance out the natural alkalinity of soap. And for baby lotion, it is slightly acidic at pH 6, which inhibits the growth of bacteria and other pathogens. So these are the questions of checkpoints 19. Okay, you can try this later. Okay, now let us look how does buffer works. The buffer components, which consist of the acid represented by Ha and conjugate base, are able to consume small amounts of added hydroxide ion or hydronium ion or hydrogen ion by a shift in equilibrium position. Let us look at this buffer solution. Consists of acetic acid and its conjugate base, okay, which is from its salt, sodium acetate. Okay, this solution has the ability to neutralize either added acid or added base. Okay, if a base or hydroxide ion is added to the buffer system, okay, the hydroxide ion will be neutralized by the acid in the buffer, causing a shift to the right. While if an acid is added, the hydronium ion or hydrogen ions will be consumed by the conjugate base in the buffer, which is this acetate ion, causing a shift to the left. The shift in equilibrium position absorbs the change in hydronium ion concentration or hydroxide ion concentration, and the pH changes only slightly. The chemical reaction in the buffer system is represented by this chemical equation. Okay, for buffer component, Ha consume the added base to produce acetate ion, while for buffer component, a conjugate base consume the added acid to produce acetic acid. Okay, the two reactions that characterize this buffer system are identical to those for the common ion effect. In order to understand the chemical reaction that takes place in a buffer solution, okay, we need to understand the common ion effect. So let us consider the acid-base properties of a solution with two dissolved solutes that contain the same ion that is called a common ion. So the common ion effect is the shift in an ionic equilibrium caused by the addition of a solute or common ion that takes part in the equilibrium. The presence of common ion suppresses or stops the ionization of a weak acid or a weak base. Okay, let us consider the mixture of sodium acetate, which is a strong electrolyte, and acetic acid, which is a weak acid. So if sodium acetate and acetic acid are dissolved in the same solution, okay, for example, they both dissociate and ionize to produce acetate ions. So sodium acetate is a strong electrolyte. Okay, so it dissociates completely in the solution. Okay, but for acetic acid, the weak acid, ionize only slightly to produce hydrogen ion and acetate ion as well. Okay, according to later Chatelier's principle, the addition of acetate ions from sodium acetate to a solution of acetic acid will suppress the ionization of acetic acid, that is, shift the equilibrium from right to left, thereby decreasing the hydrogen ion concentration. Thus, a solution containing both acetic acid and sodium acetate will be less acidic than a solution containing only acetic acid at the same concentration. Okay, as you can see here, the shift from right to left in equilibrium of acetic acid ionization is caused by the acetate ions from the salt. Okay, so in this case, acetate ions is the common ion because it is supplied by both acetic acid and sodium acetate. So this acetate ions is called a common ion. Okay, now let us look at this slide. As I mentioned earlier, when acetic acid is dissolved in water, it will dissociate slightly, since it is a weak acid, to produce some acetate ion. Okay, when sodium acetate is added, it provides a source of acetate ion, and the equilibrium will shift from right to left or to the left, according to Le Chatelier's principle. So acetate ion is common to both solutions. The addition of acetate ion, the common ion, reduces or suppresses the percent dissociation of the acid. So this is what we call the common ion effect, where there is a shift in equilibrium caused by the addition of compound having an ion in common with the dissolved substance. Okay, let us look at this table on the effect of added acetic ion on the dissociation of acetic acid. Okay, you can see here as the concentration of acetic ion increases, the percentage of dissociation decreases. Okay, the percentage of dissociation can be calculated by using this equation where the concentration of acetic acid dissociate divided by concentration of initial concentration of acetic acid multiplied by 100. This is a checkpoint 20. You can try it.
Alright, so for this buffer solution, okay, so these are all the outcome. The pre-recorded video just now already explained this, acidic and basic buffer in terms of acid-base component, explain common ion effect, and explain qualitatively on how buffer solution works when acid or base solution is added. Okay, so later, the second video, we are going to learn on how to calculate pH. But before that, let's have a look what is buffer. Okay, so for types of buffer, this buffer solution itself, it must contain, okay, it must contain either, there are two types. It is either acidic buffer or basic buffer. But for example, acidic buffer, it must contain the mixture of weak acid and its conjugate base. Okay, so this conjugate usually that is coming or supplied by salt. And then for basic buffer, okay, the buffer component of this basic buffer is weak base and its conjugate acid. Okay, so this conjugate acid is coming from salt. For example, this one, okay, formation of a buffer. So you have this acetic acid, okay, acidic buffer. So acetic acid react with combine with sodium acetate. So this is the component of weak acid. Okay, this is the component of weak base, conjugate base of this weak acid that is coming from salt, CH3COO minus. So to make a buffer, okay, any buffer must contain weak acid and its conjugate, or weak base and its conjugate. Okay, so dia tak boleh datang daripada strong acid and its conjugate. For example, HCl dan Cl minus. Even though Cl minus is a conjugate of this acid, but then it is a strong acid, so it cannot act as a buffer. Okay, it must be weak acid and its conjugate, or weak base and its conjugate. Okay, so let's just consider this titration. Okay, there is a point in the titration. Okay, let's say this one. Okay, this is the titration curve. Okay, there is a point in the titration where you are asked, or you need to determine where is the buffer region. Okay, so either let's say kalau saya bulatkan, let's say dia adalah kat sini, atau dekat sini, atau dekat sini. Okay, kalau saya label katalah 1, 2, 3, determine where is the buffer region of this titration. Contoh. Okay, so how do you determine the buffer region in any titration? Okay, so do remember that buffer, it is a combination of weak acid and its conjugate. So keadaan di mana weak acid ada dan dia punya conjugate ada, maka tu adalah keadaan buffer. Sama juga if you use weak base, keadaan di mana ada weak base dan dia punya conjugate, maka itu adalah buffer. So balik kepada titration, okay, contoh you titrate HCl dengan kita perlu sesuatu weak base, katalah ammonia. Okay, katalah ammonia. So ammonia NH3 plus HCl, it will produce NH4Cl. Salt yang supply dalam salt ni ada NH4 plus dan Cl minus. So keadaan di mana NH3 exists together with its conjugate NH4 plus, itu adalah keadaan buffer. So in this case, katalah you mula dengan ammonia kan, sebab ni pH start dengan basic range. Okay, so bila you apa ni, construct the ICE table for mole, katalah ammonia initially you ada sebanyak katalah you ada 1 mol. Mana? 1 mol ICE. Okay. This one you ada 1 mol. So untuk dia capai equivalent point, you perlu tambah HCl sebanyak 1 mol juga. Okay, katalah you tak tambah dia 1 mol. You tambah dia 0.5 mol. Maka so ni kosong, ini tak ada apa-apa. Okay, ini initially tak ada apa-apa, ni pun tak ada. Bila you tambah 0.5 mol HCl, so ammonia dia akan react sebanyak yang samalah 0.5 mol. So dia ada baki 0.5 mol here. There is nothing left for HCl sebab dia habis react dengan ammonia. Tapi salt yang dah diproduce adalah sebanyak 0.5 mol juga. Okay. So sebab dia dah react sebanyak 0.5 mol. Ammonia ada baki, HCl habis digunakan, and salt, how much the acid and base has reacted, so that much will be produced. So at this point, ni contoh je lah at this point, so daripada you tambah, okay, initially you ada siapa dia ni, ammonia, you tambah acid sikit, so dia dah terbentuk sedikit salt, you tambah acid terbentuk sedikit salt, you tambah, okay, sehingga nak sebelum sampai dekat equivalent point meaning that kalau you ada 1 mol, acid pun you tambah 1 mol. Sebelum nak sampai equivalent point, at any point of this reaction, kalau saya bulatkan kat sini, ini adalah dikatakan buffer region of this titration. Okay, kenapa dia buffer region? Sebab at that point, dia ada dia punya weak base and its conjugate. Okay, sebab bila dia dah sampai equivalent point, yang ada hanyalah salt and H4Cl. Okay, at equivalent point yang ada hanyalah salt. Tapi sebelum dia produce, everything converted to salt. So at this point of reaction, dia ada NH3 dan NH4 plus present bersama. So maka tu adalah buffer region for this type of titration. Okay. Once dia dah sampai equivalent point, kalau you tambah lagi acid, so dia akan ada NH4Cl dan HCl. Okay, kalau you tambah lagi HCl, tambah lagi. Okay, ini yang saya plot. Okay, yang number 1, yes, it is buffer region. Yang saya label yang number 2, it is not buffer region. Kenapa? Macam saya cakap tadi lah, buffer dia mesti weak acid dan dia punya conjugate atau weak base dan dia punya conjugate. In this case, dia ada acid dan dia punya conjugate. Tapi sebab dia strong acid, maka dia bukan buffer region. Okay? Yang tengah-tengah ni memang tidak lah. Okay? So biasanya sama ada sebelum titration, sebelum equivalent point atau selepas equivalent point. Tapi yang mana satu is the buffer region depending on what species present. Okay. So second example, katalah saya ambil Okay, katalah saya ambil mana saya punya ni tadi. Okay, this curve. Okay, contoh. Let's say this is the reaction between NaOH dan CH3COOH. Let's say CH3COOH plus NaOH. So it will produce CH3COO and A, salt. So you start dengan katalah CH3COOH. Sebelum sampai equivalent point, ni sama case lah. Katalah you ada 2 mol originally present. So ICE. So sebelum nak sampai, kalau you add 2 mol, dia akan reach equivalent point. Last water. Okay, tapi sebelum nak sampai 2 mol, sebelum sampai sini, alright, so at any point of this, ini adalah dikatakan buffer region kerana, okay, katalah you tambah 1.5 mol of sodium hydroxide. So maka there is 0.5 mol left for acetic acid, but there is nothing left for sodium hydroxide. How much salt is produced is this much. Sebanyak mana yang dia dah react tadilah. Okay. So along this point, okay, so tu adalah dikatakan buffer region kerana the species that exists is your weak acid and its conjugate yang datang daripada salt. Okay, so in this case weak acid adalah CH3COOH. The conjugate yang datang daripada salt adalah CH3COO plus, tipu, minus. Sorry, it is minus, okay. CH3COO minus. Alright, so at any point of the reaction, yang mana kalau dia exist, dia punya weak acid and its conjugate base yang datang daripada salt biasanya, so tu adalah buffer region. Tu je lah saya nak highlight, okay. It depend on what type of acid and base use in your reaction, okay. So this is the application of buffer, and then yang lain tu tak ada apa-apa sangat nak highlight. Yang Dr. Saliza cakap dalam pre-recorded video tu dah memang detail, dah bagus dah. Okay, so okay, let's try to answer this checkpoint 19. Which of the following is a buffer solution? Okay, consider one by one. Okay, we need buffer component either weak acid and its conjugate base atau weak base dan dia punya conjugate acid. So A, the first one. Is it a buffer solution? So you just have to look at this. Is this a weak acid or strong acid? Weak acid. So conjugate, okay, HCN dan CN minus yang datang daripada salt KCN. So both menepati ciri-ciri buffer, yes. Maka A is a buffer solution. Okay, B, 0.2 molar CH3COOH. So obviously dia hanya ada satu je dan this is a weak acid. So dia tak ada dia punya conjugate, maka this is not a buffer. Alright. For C, HNO3 and ANO3. HNO3 is a strong acid. Even though this supply dia punya conjugate base of that acid, but then it cannot act as a buffer because it is a strong acid. Okay, so this is not a buffer. KCN, is it a buffer solution? No, because KCN is only salt. Okay. Suppose KCN dia mesti hadir dengan HCN, dia punya weak acid. So this is not a buffer solution as well. E, is it a buffer solution? HCl strong acid, obviously cannot, even though it provide the conjugate base of that acid. Okay. So question number 2, identify the mixture that yield a buffer solution when equal volume of the two solution are mixed. So this one is a strong acid, strong acid, strong acid, strong acid. This is the only weak acid. Okay, even though it provide all the conjugate, but then all this is a strong acid, it cannot act as a buffer, meaning that the answer is E. Okay, because this is weak acid and this is the conjugate base that is coming from sodium fluoride salt. Faham? Ada soalan nak tanya for this buffer? Tak ada? Okay, let's check the answer. Betul semua. Alright, so kalau tak ada, moving forward to the second video. Okay, before we finish up our class, we need to finish up this chapter 3 because next week you gonna have your test and semester break, midterm break, sorry. And then after that, kita masuk chapter baru, chapter 4. Okay, so bertambah lagi sikit ya.
Solutions. How does the buffer works? The common ion effect, the shifting of the equilibrium, and now you are going to learn on how to calculate the pH of a buffer solution. Okay, let us look at this example of acidic buffer solution. Okay, consider a buffer solution containing acetic acid and its salt, which is sodium acetate. Okay, in the buffer solution, the concentration of sodium acetate is 0.11 molar, while the concentration of the acetic acid is 0.09 molar. Okay, calculate the pH of this solution. Okay, now I'm going to explain on how to calculate the pH of a buffer system using the ice table before I introduce you the Henderson-Hasselbalch equation. So let us first start with the chemical equation. Okay, when you add the weak acid to liquid water to produce acetate ion and hydronium ion. So the hydronium ion is controlling the pH. Okay, so let us set up the ice table with initial, change, and equilibrium on the left side. And since you know the initial concentration of the acetic acid, so we just write down 0.09 here. Okay, we can ignore the concentration of the liquid water. And what makes this ice table different from the regular ice table that you have learned before is here you know or you have the initial concentration of the acetate ion contributed by the salt, which is sodium acetate. So the initial concentration of sodium acetate is 0.11. So just write down 0.11 here, and we don't have the hydronium ion concentration yet, so just leave 0 there. And for the change, we are going to lose the value of x here. Okay, so it will be negative x, and we are going to gain the amount of x here, so plus x, as well as the amount of the hydronium ion, so plus x. So at equilibrium, okay, just sum up the I and C row, okay, to have 0.09 minus x here, and 0.11 plus x, and x for hydronium ion. Okay, next, set up the equilibrium expression, Ka. Okay, as you know that Ka is the concentration of the products over the concentration of the reactant. Okay, since the Ka value is given in the question, so just plug in the value here, which is 1.8 times 10 to negative 5. Okay, next, Okay, from the equilibrium expression, which is Ka, we are going to plug in all the values, okay, of the hydronium ion concentration at equilibrium, conjugate base concentration at equilibrium, and acetic acid concentration at equilibrium. And the Ka value here is 1.8 times 10 to negative 5. Okay, here you are going to solve X, and since it's pretty nasty here, so you are going to make an assumption. And if you look here, that since Ka value is very small number, we can neglect the X. Alright, so solve X, and you get 1.5 times 10 negative 5. So what is X is actually the hydronium ion concentration at equilibrium. Okay, with that you can calculate the pH of the buffer solution by using this equation. pH equals negative log hydronium ion concentration. Okay, and to give the pH of 4.82. So this is the way on how to calculate the pH of a buffer solution by using the ice table. We can also calculate the pH of a buffer solution, okay, by using an easier method, okay, which is Henderson-Hasselbalch equation. Buffers are prepared from conjugate acid-base pair in which the ionization is approximately equal to the desired hydronium ion concentration. Okay, now let us look on how to derive the Henderson-Hasselbalch equation. Okay, let us start with preparing the chemical equation when we have an acidic buffer solution, okay, containing weak acid. Okay, when you add it in liquid water, it will produce hydronium ion plus the conjugate base. So the acid dissociation constant, which is Ka, is the concentration of the product over the concentration of the reactant at equilibrium. Okay, when you rearrange it, okay, you will get H3O plus on the left side. Okay, equal Ka Ha over A minus. Okay, taking negative log on both sides. Okay, you will get pH, which come from negative log hydronium ion equal pKa plus log of the base species over the acidic species. On the other hand, okay, you can also use the mole value, okay, in this Henderson-Hasselbalch equation. Okay, since the concentration is equal to mole over the volume in liter, okay, and you will get this mole of conjugate base over volume in liter over mole of Ha over volume in liter. Okay, you can cancel this out, okay, leaving mole of A minus over mole of Ha. So these are the equations that you can use in order to calculate the pH of a buffer solution. Okay, this will be the general equation for Henderson-Hasselbalch. Okay, pH equal to pKa plus log, okay, the base species over the acid species, concentration at equilibrium. Okay, other expressions are as follows. So in acidic buffer, you can use this equation as has been described previously. So pKa plus concentrations of base over concentration of acid, okay, at equilibrium. And for basic buffer, you can also use equation where you use POH equals, okay, here you are going to use pKb plus log of the concentration of acid over concentration of base species at equilibrium. Okay, don't forget, okay, to convert it into pH. Okay, once you get the POH, okay, to calculate the pH is 14 minus the POH, so that you will get the pH of the buffer solution. Okay, what is important here is to identify the acid base species in the buffer system. Otherwise, you will get it wrong. Okay, now let us look on how to calculate the pH of a basic buffer. It consists of 0.3 molar of ammonia and 0.36 molar of ammonium chloride. Okay, the pKb value is given here, which is 4.75. Okay, let us start with expressing the chemical equation. Okay, here ammonium will become the reactant, okay, to produce H plus ammonia. So let us start by using the first equation on how to calculate the pH value of the buffer system. Okay, I'm going to use the first equation, which is pH equal pKa plus log of the base species. Okay, base over concentration of the acid species. So now let us determine what will be the base. Okay, so it will be the ammonia, and while the acid species will be the ammonium. Okay, with that, let us plug in the values. So pKa is 14 minus pKb, since the pKb value is given there. So 14 minus 4.75 plus log concentration of ammonia over concentration of ammonium. So you will get 9.17. Okay, you can also use the second equation in order to calculate the pH of a basic buffer solution. So please keep in mind that here you are going to use pKb as you are using POH here. So for POH is pKb plus log. Now the upper part will be the acid species. The lower part will be the base species. Okay, POH equals pKb, which is 4.75 plus log 0.36, okay, of this ammonium over the concentration of ammonia. So you will get a POH of 4.83. Okay, and finally calculate the pH. Yes, you know that pH is 14 minus POH. Since you have a 4.83 for the POH, so 14 minus 4.83, we also get 9.17. So now let us compare the values. Okay, this will be the question 1 for checkpoint 21. Question 2 for checkpoint 21. You can try this later and discuss the answer with your lecturer.
Alright, for this calculation of pH, okay, either it's just a bit differ from the one that you have learned previously, okay, when you construct the ICE table, most of the time, if you have this equation, CH3COOH in water, produce back the conjugate, most of the time we only have this concentration, okay. But here, before this, the calculation here is 0. So because there is no buffer, it only with acid or any salt, okay. But then in this buffer, the differ is you have two value. Okay, so there are two types of calculation. Either you want to use this method, ICE, and then so for X, by using Ka, you will get this pH value. But for me, it's easier if you use this Henderson-Hasselbalch equation. But then it's just the same, okay? If you want to use this method or Henderson-Hasselbalch method, so you suppose you will get the same pH value. Okay, for Henderson-Hasselbalch equation, I just want to highlight, okay. This is the general equation for Henderson-Hasselbalch, okay. Either in acidic buffer and in basic buffer. But then, if you want to use only one, pH which is equal to pKa log base over acid, you can use actually in both type of buffer. Okay, because for example, let's say you have this system CH3COOH plus water that will produce CH3COO minus and H3O plus. Okay, so in order to calculate the pH of this buffer system, pH is equal to pKa. So pKa nak refer kepada siapa? Mesti acid dalam buffer komponen tersebut. So in this case, this is the acid, this is the base. Okay, so pKa of this acid plus log concentration of base. So this is the find the concentration of this base and divide by concentration of acid. This is the acid. Okay, but if you want to change, you want to use the same Henderson-Hasselbalch equation but in basic buffer. Yes, you can. For example, let's say you have ammonia plus water. Okay, you will get here NH4 plus OH minus. Okay, so if you want to use the same formula Henderson-Hasselbalch for this basic buffer, you just have to know that this is the base in your buffer system, this is your acid in your buffer system. Okay, NH4 plus is the conjugate acid of ammonia, NH3. So pH is equal to pKa. So you need to find pKa, of course, for the acid. So you need to find what is the Ka for NH4 plus to convert to pKa. Okay. Of course, in the question, you will not be given, most of the time, you will not be given the Ka for NH4 plus. Alamak, terpadam. Okay. But then you will be given Kb for ammonia. But that's okay. You just have to find what is the Ka for NH4 plus. After you get the Ka for NH4 plus, you need to find the pKa, negative log Ka, okay, for this. And then use the same, plus log base over acid. So this is the base in your system. This is the acid in your system. So that's it. You will get the pH immediately. So it actually can be used in both systems, but you just have to identify which species is the acid in your system and which species is the base in your buffer. Okay. So I think that's all for the calculation of pH, and then try to answer this checkpoint. In order for you, the last part of the of this chapter, okay, the last pre-recorded video is actually to prepare buffer, and it discuss buffer effectiveness. So for that one, I leave it for you to watch it yourself. Okay, so after you watch it, make sure you try to answer this checkpoint. Okay, all this checkpoint involved. Alright, so this is the effectiveness of buffer. Okay, this is the summary of this chapter. Okay, so it's actually once kita dah sampai buffer, sebenarnya there are 4 types. Okay, 4 types of calculation of pH. Strong acid and strong base, nak kira pH you boleh dapat directly. Dia punya sama ada concentration of H3O plus or concentration of OH minus directly from the acid and the base species. Okay, so the concentration of H3O plus is just the same as the concentration of acid. Concentration of OH minus is just the same as the concentration of base. Okay, but then the second one yang kita belajar is under this category. Okay, so weak acid, weak base. So weak acid, weak base, you need this info, Ka, Kb, in order for you to find the concentration of H3O plus and OH minus. So H3O plus, you are going to use this formula in weak acid, weak base. Okay, C times Ka. And then the third one we learn is actually the titration. After weak acid, weak base sebenarnya ada salt. So salt ni sebenarnya kita guna dalam titration. Okay. So for titration at equivalent point, the only species present is your salt. Salt you need to dissociate. Dissociate and then hydrolyze. Choose which ion that will further hydrolyze. And then this part sebenarnya sama dengan weak acid, weak base punya calculation. And then the fourth one yang just now kita tengok adalah buffer. The easiest method to calculate pH is for buffer is by using Henderson-Hasselbalch equation. You can apply this equation in both either acidic or basic buffer. But then kalau tak nak macam in basic buffer, tak nak guna pH is equal to pKa log base over acid, yes, you can use this one. POH which equal to pKb log acid over log base over, kenapa terbalik tu base over acid. Base over acid, acid over base. Sekejap, nak check. Okay, betul-betul. Okay, follow yang ni. Kalau you guna yang POH, dia mesti PKB. Dia mesti terbalik daripada yang ni PKB. Kalau yang asal base over acid, ini mesti conjugate acid over base. Okay, dia mesti terbalik. Sebab dalam summary tadi, macam tak terbalik. Okay, so BOH is the base kan? Ni salah betulkan dalam you punya slide summary. Ni betul, ni base over acid. Ini mesti acid, bukan BOH. BOH for base. Acid over base. Macam tu. Alright. So, do you have any question before we finish our class? No? No one left in my class?
No question, madam.
Okay. Alright. So, tak ada soalan Alright. So, I think this is our last meeting before your test and your break. So, good luck for your test. For those who haven't take the quiz 2 yet, so good luck for your quiz 2 as well. Quiz 2 berapa orang ni dah ambil ni? S34 seorang dah jawab. S33 seorang juga dah jawab. 2 orang. Seorang tengah jawab. Oh, jawab tengah kelas Bagus. Alright. So, I think that's all for today. Good luck for your test. Do your best. Jangan panik. Make sure guna, kalau boleh, ink pen, gel pen, so that your answer will be clear enough for us to see and to mark. Okay. Jangan guna pensel. Siapa guna pensel, susah nak cakap. Okay. Okay. So, that's all for today. Assalamualaikum.
Waalaikumsalam. Thank you, madam.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Waalaikumsalam. Thank you, madam.
Waalaikumsalam. Thank you, madam.
Alright. You're welcome.